Hello there. This video is on section 6.3, and I'm going to show you how to find volumes of regions that are rotated about an axis, and we're going to be using the shell method. The previous video was using the disk method, and so we're going to be solving very similar problems using an alternate method called the shell method. I'll show you how it works. I'll show you why it's called the shell method. Our strategy will be also just like before in 6.1 and 6.2, is to slice our region into infinitesimally thin rectangles. To do the shell method, we're always going to slice the rectangle parallel to the axis of rotation. We're going to write down the differential that represents the width of this this very small width of this rectangle, and then we're going to go from there and find the volume. Let me show you what this looks like on a couple of examples. I have example A here. It says use the shell method to find the volume of a solid by rotating this particular region given by four boundaries. It goes around the axis x equals 0. And then I'm also going to do it around the axis x equals -1. I'm going to do it around the axis y equals 0. And lastly, I'm going to do around the axis y equals 5. So same region, revolve lots of different places and ways. All right, well, first of all, let's get a look at what this region looks like. I'm going to be using Desmos to graph these four functions. I've already typed them in. Here's the square root of x. Here's a 1/2 x. You can see they kind of make this like a little sliver of a shape. There's a 0, and there's 4. And we are indeed going from 0 to 4. So 0 and 4 are the endpoints, but we can already see those are the endpoints because that's where the two graphs intersect. Okay, so on the right-hand side is this orange thing. On the bottom is purple. On the left is red, and on the top is green. And that's the region bounded by those four graphs, four curves. Okay, so I'm going to draw this. It goes from 0, 0 to 4, 2. Just doing a little sketch here to show one's work. If you're using technology, no biggie, just show a little bit about what you got on technology. I'm going to move this over a little bit because I know I ran out of space last time, so I'm just going to hog the middle of the screen so I don't run out of room. 0042, and one of the graphs was kind of like this. The other graph was kind of like this, and we get that region right there. Okay, so that's our region, and we're going to be revolving this around. Well, the first one is x equals 0. X equals 0 is right here. It also represents a line, and the line is where x equals 0, which is also called the y-axis. So this is x equals 0, and we're revolving around that axis right there. Now, to use the shell method, we must slice our region with a rectangle which is parallel to the axis of revolution. So because my axis is vertical, my rectangle must also be vertical to use the shell method. If I take this rectangle and I revolve it around, the distance from here to here has to be a mirror image, distance from here to here. And I get my slice, sort of mirror image my slice. And this is kind of like a circular shape because it's going out, out and around. It makes a circle like this and like this as well. So that's kind of the shape I'm going to get for my one slice that's been revolved around the line x equals 0. All right, so if we find the interior volume of this slice and we find the interior volume of other slices, we're going to be double counting things. So this is not how the shell method works. What essentially we're doing is we're going to be finding the outside surface area times the thickness. This is as if we're doing layers of a roll, like a paper towel roll. If I find the surface area times this really small thickness of this first sheet of paper towel, and then I find the same of this slightly smaller radius. I mean, as I pull this out, the radius is getting smaller and smaller. And so the idea here is I'm finding the surface area of consecutively smaller and smaller areas on this roll of paper towels. And that way I'll find the total volume. If I have all of these, paper towels, then I find the volume of the whole thing. So that's the idea of the shell method. And this shape of a paper towel rolled up is called a cylinder. So I'm going to have to find the surface area of a cylinder times the thickness of a paper towel, which is either dx or dy, right, depending on how I orient it, right? And so I need to find the surface area times the thickness, and that will give me the volume of one of these sort of slices, one of these cylinders, one of these paper towel segments, and then I'm going to do it for all the different paper towel segments. So that's the way the shell method works. So for this one little slice here, I'm going to find the surface area or the volume, which is the surface area times the thickness. And then I'm going to do that for all the slices and add them up. And that's how I'm going to find my volume. All right. So let me just move this over here. All right. So for that one little slice, the volume of the slice, SLI slice, the volume of the slice, well, it's going to be the surface area of a paper towel. The surface area of a cylinder is just 2 pi RH. You may remember that from your geometry. But it's also like the circumference of the circle, 2 pi r times its height, so 2 pi r around the circle, and then the height. That's how you find a cylinder. And then to make it a three-dimensional object, you have to multiply how thick it is. So that's going to be our volume of a slice. And to find the volume of the whole thing, the volume of the total thing, we're just going to do this 2 pi r times 2 pi r times thickness, and we're going to integrate over all possible slices. All right, so let's get into some details about what's going to happen. First of all, notice that in order to do the rectangle parallel to the axis of revolution, I had to make the slice up and down, right? So my vertical slice parallel to my vertical axis of revolution. That means that the thickness, the very small, infinitesimally thin rectangle, the thickness is in the x direction. So that's got to be dx thickness. So this thickness here is got to be dx, which means eventually all my other stuff has to be in terms of x. 2 is a number, pi is a number, we don't care about those. We need the r, the radius, and the h, the height, in terms of x. All right, so let me zoom in a little bit. Maybe it'll be easier for people to see what's going on here. But for this little cylinder shape right here, the middle of the cylinder, middle of the circle, is right there, and where the axis of revolution is. And the radius always goes from the middle to the outside. So here's where the green thing right here is where my slice is. So no matter where I choose the middle, going to the outside always goes to where this function is right there. Okay, so that's where it is. Right there. All right, that's that distance right there. Same distance all along. I'm going to draw this because it's just less confusing just to draw one right here. So what is this top function? This top function is the y equals square root of x function. And what's that distance right there? That's an x distance. How do I know it's x? Because everything that moves in the horizontal direction is an x distance. So this is an x distance. So it's going to be radius is x. Right, the distance from the middle to where the slice is. So what about the height? Well, the height is the height of our cylinder, which is this here to here. That's a vertical distance. So vertical distance has to do with y's, right? All vertical distances are measured in terms of y. It's between two things. It's between the square root of x thing on the top. And what's the bottom thing that's guiding it? Well, that's the other function, 1/2 x. So this vertical slice in red is between, it has a top part of y equals square root of x and has a bottom part of 1/2 x. So how do you find the distance between two things? You subtract them. So we're going to subtract this guy. We're going to subtract this guy minus this guy to find the height, that red height. So what are those two things? Well, it's the y big minus the y little, but we need everything in terms of x, right? Because our slice is in terms of dx. So instead of writing some y's there, let me write the equivalent thing in terms of x. So for the top one, the equivalent thing is root x. That's the y which is equal to root x on the top, and the y on the bottom is equal to 1/2 x. So I'm just subtracting the y values, but I've written in their formulas instead of writing in y. I have to have them all in terms of x, so I'm going to be using the equivalent versions of y, square root of x, and 1/2 x to subtract those to find the height. So the height here is two y values subtracted. The radius is literally just the distance x, because it's from the thing all the way to the axis, and then 2 and pi are the constants. All right, well, if we know how to find the volume, if we know how to like find the radius and the height things, we know how to find the volume. All we have to do is make sure everything's in terms of x, and we have to make sure our limits of integration are in terms of x as well. So we need to look at our region and find the smallest x value in our region and the largest x value in our region. Well, our x's go right and left. This is the smallest x value at 0, and the largest x value is at 4. So we go from x equals 0 to x equals 4. And that's the volume of this region. This region revolved around the line x equals 0. So it's sort of three-dimensional shape using this thing called the shell method. The shell method uses 2 pi RH times the thickness. And if you remember from our previous section, we did the disk method, which was pi r squared times the thickness. So pi r squared times thickness, or 2 pi RH times the thickness. That's the two different formulas, the two different cross sections we get for the disk method and the shell method. All right, not much to do here, but just do some simple algebra here. So 0 to 4, I'll stick to 2 pi on the outside. We have to distribute x times root x is x to the 3/2. X times x is x squared. We get a dx here. We anti-differentiate, plug in some numbers, and then you got the answer. So x to the 5/2 divided by 5/2 is the same as times 2/5. And here I get 1/2 x to the 3 over 3. So it's going to be eventually over 9. We have to plug in the 4 value. We have to plug in the 0 value. We have to subtract, and we get our answer. As you may know, if you've watched my previous videos, I'm not big into using video time to do all the calculations. I'm going to leave that up to you unless you really want me to do it, and then you can just let me know, and I can give you the answer, or I can show you through Zoom or something how to get all the numbers to work out right. All right, so that was the answer for x equals 0 as our axis of revolution. And I'm going to do the exact same region. We're just going to spin it around different things. So we're going to spin around x equals -1. We're going to spin around y equals 0. We're going to spin around y equals 5. We're going to do various axes of revolution so you can sort of see the pattern of how this works. And also some of them are a little harder because you're not doing a standard axis revolution. X equals 0 and y equals 0 are the y and x axes. X equals -1, y equals 5, a little bit different, but it's the same strategy. All right, so let's do x equals -1. All right, so get my region here. 4, 2, top 1, bottom 1, and we're revolving around the line x equals -1. The x-axis is the horizontal axis, so x equals -1 is over here. This is where x equals -1 is. And so this is my axis of revolution. And to do the shell method, I have to do parallel. So there's my vertical parallel to that. It has a thickness of dx. I revolve around. So this distance from here to here has to be the same because it's symmetrical. So I get the same distance, and I get my little rectangle over here, and I get this big old circle thing on the bottom, like that. Okay, so I need to figure out the formula. Whoops, put that back. I need to figure this out, the formula for the shell method for the volume. Okay, so we already know that the formula for the volume of a slice is just 2 pi RH times how thick it is. And then to find the volume of the whole thing, you're just going to add them all up together using an integral. All right, so the hard part maybe comes down to visualizing what's going on and finding out the r and the h in thickness. The thickness we already know is dx because we sliced it vertically. And we have to find the r and the h. So the r is always, a radius of a circle. So the center of the circle is where the axis of revolution is right there. And we have to go all the way out here. So that is a horizontal distance. It's not just x. Some people say, oh, it's x, but x always goes like to the axis, right? Whenever you measure like x distance, like I say x is 4, 4 goes from 0 to 4. It doesn't go from -1 to 4, right? I'm going from -1 out to this place over here. So whatever the normal x distance was, it's 1 further away. Or if you want to just subtract, the two things, it's the x distance minus the -1, which is x plus 1. So that distance, that horizontal distance, that radius is going to be x plus 1. In the previous problem, you might notice that the radius was just x. Now it's 1 bigger because we've gone further. All right, what about your height? Your height goes from here to here. That's just the height of the rectangle. That's the same as the height of the rectangle in our previous problem. It hasn't really changed. The fact that we're rotating around -1 did not change the height of the rectangle. It's still going from here to here, which is between two functions. So to find the distance between two functions, you just subtract them. So we get this top function, our y big function, and we get this bottom function, our y little function. You subtract those two, and that's going to be the height, which is exactly the same as the calculation before, square root of x minus 1/2 x. So that's your height. And your thickness is, of course, dx. And then to find the volume of the entire thing, instead of just trying to find the volume of that slice, to find the volume, total volume, then all we do is just integrate it. And we integrate it over the span of x values for our region. Our region goes from here to here. The x values go from 0 to 4. I know there's a -1 there, but remember, it's talking about our slices. And the leftmost slice of our region is over here at 0. Our region doesn't exist over here, right? Our region isn't near -1. Our region starts at x equals 0 and ends at x equals 4. That's why x equals 0 and x equals 4 are the numbers there, because they represent the smallest and biggest x values of our region. So this is the volume for our region revolved around the line x equals -1. All right, very similar. Maybe if you have the idea, you just have to sort of draw it out and see what if anything changed. In this case, the radius got bigger. It got exactly 1 bigger. And so that ended up just changing that part of the formula. All right, the next thing is we're going to be doing this thing revolved around y equals 0. So same deal for 2. Top part, bottom part. And we're going to do the axis of y equals 0. Y equals 0 is like at the point where y equals 0, it's called the x-axis. So this is y equals 0. We're revolving around this thing right here. Okay, so that's our axis of revolution. In order to use the shell method, our slices must be parallel to the axis of revolution. Here's a parallel slice. The thickness of this parallel slice, it's really a very, very small change in the y direction. That's how infinitesimally thin this rectangle is. That's called dy. So eventually our function is going to, our integral is going to be in terms of dy. So everything's got to be in terms of dy. All right, nonetheless, we're going to revolve this around the y equals 0 line. So whatever this little thing right here, the distance has to be equal, has to have like a mirror image. So whatever that distance is there has to be the same as this distance. So we end up getting this sort of mirror reflection of our little like slice there. And if you want to make it look three-dimensional, you can kind of put a circle here and a circle here. So that's sort of our shell. That's our cylindrical shell. The one paper towel, roll, whatever, that we're going to find the volume of. And then we're going to do all the other possible slices. These are all horizontal slices. So there's slices here, there's slices all over the place. All right, so let's find the volume of this one slice. So the volume for this one slice, well, we know it's 2 pi RH times the thickness. what is the radius? Radius is always the distance from the middle to the outside of a circle, right? So the middle is where the axis of revolution is. So here's my axis of revolution right here. I go up. That's a vertical change, right? That vertical change, well, any vertical change is y, right? There's some y distance going on there. I have to subtract the two y values, but this is y equals 0. So this is just a y height. So the radius of this thing is y. So that's the radius. The thickness, by the way, is dy. So we don't have to change this into x's. We want everything in terms of y's, and the radius is y, so we just leave it alone. The height would be the height of the cylinder. If you can see, since our cylinder goes like this, that's the height of our cylinder. Our cylinder's turned on its side, but you hopefully can still see that. So the height of the cylinder is an horizontal distance. So it's got to be an x distance. It's between two functions. It's between this function and this function. This top function was square root of x. Bottom function was 1/2 x. And so I have to go the between two functions, but I have to do the x values between two functions. It's got to be the big X minus the small x. We're trying to find the distance between two things. To find the distance between two things, you just subtract. It's going to be the big X value minus the small x value, right? Because it's got to be x direction. But I have to put these in terms of y. Everything has to be in terms of y because our dy there. So I need to put these in terms of y. How do I do that? Well, I was given the formula y equals square root of x tells us that y is the same as square root of x. So if I square both sides, that means x is the same as y squared, right? I mean, I can manipulate this equation all day long. I want to know what the x is, so that's y squared. What about this one over here? This is y equals 1/2 x, and I could just solve for x. Multiply both sides by 2. So one of these things is 2y, that's the x version of this straight line thing. The other one is y squared, that's the x version of this curvy thing. Which one is bigger? We have to do big minus small. Well, the bigger x value is the one that's farther to the right. Remember, as you go farther to the right, you get bigger x values. So this one on the right is the bigger one. That's the 1/2 x or the 2y guy. So this has got to be 2y. Smaller one is over here, closer to the y-axis. And that was the y equals square root of x, which we rewrote as x equals y squared. So putting these things in terms of y's, we get this minus this. We still have our dy. We still have our y. We still have our 2 pi. If we integrate this over all possible y values, then we get the total volume. So the volume, total volume is equal to this. We just have to find all the possible y values of our region. So our region goes from down here all the way up here. The smallest possible y in our region is right here at 0. And the highest or largest possible y value is up here at 2. That's 2 right there. So we go from y equals 0 to y equals 2. And this right here is how you find the volume of the region revolved around the line y equals 0 using the shell method. All right. And again, I'm going to let you do the actual integration if you want to complete and get the answer to that problem. All right, and I have one other one with this this region, and that's revolved around the line y equals 5. So if you have not already thought about pausing the video, maybe this is a good time to try. I mean, y equals 5 isn't the easiest one, but if you kind of get the idea of what's going on, I think you got a good shot at it. We're going to take our exact same region, right? Actually, I need to make it a little bit further down because I know I'm going to y equals 5. All right, so I got my 0, 0, my 4, 2. I got my my curvy thing on top. I got my straight thing on the bottom. And my axis of revolution is y equals 5. That's my axis of revolution. So I have 5 up here somewhere. Let's say 5 is here. And that's the y equals 5 is a horizontal line. So this is going to be my axis of revolution right here. And so you're going to slice this thing up and revolve it around there to use the shell method to try to find the volume of that thing. So if you want to give it a go, this is a good time to pause and see if you can figure out, or if you can get somewhere, you'll at least know what you got so far and where you got stuck, and then you can watch the video to see how you might get unstuck. Or you might get all the way, which would be fantastic. And we'll see. We'll see. Okay, well, if you don't want to pause and try it yourself, or if you have and you're coming back, welcome back. And I will show you the solution for this problem. All right, because our axis of revolution is horizontal, we need our slice to be horizontal, because the cylindrical shell method has slices that are parallel to the axis of revolution. This is a dy slice because it's a vertical thickness of like almost nothing. The infinitesimal width here is a y change, dy. And then I'm going to do some symmetrical things. So I can imagine this distance from here to here has to be the same as this distance from here to here, right? So there's got to be like some mirror image of this little rectangle piece up here, right? And then I'm just going to kind of connect this little piece and connect this little piece. And there's my cylinder. Can you see the cylinder? That's like the height. And then the radius goes from the middle to up here, right? That's the radius of the circles, like up and down. So the circle's there. We got a radius going there. Where I guess it would be easier if I do the radius to the actual region. The region, my friends, is down here. And that is the radius, but it's easier to figure out the radius going actually to the region. Since we know everything about the region, let's call this the radius from the axis of revolution to the outside of the circle, which is the same no matter what, but let's use the one that's actually touching the region, so it'll be easier to find. All right, and the volume for these shell method problems for a slice, it's always the same. It's always a cylindrical shell, which is 2 pi r h times how thick it is. And we know the thickness already is dy. And so all we have to do is figure out, we know the 2 and the pi. All we do is figure out the radius and the height. So as I mentioned before, the radius goes from the middle of the circle, or the axis of revolution, to the outside. So it's this distance from here to here. How do I find that distance? Well, it's between two things. It's between here and here. So when I want to find a distance between two things, I subtract. So this top guy up here is y equals 5. So that's one thing. And the bottom thing down here, well, if you remember from the previous problems, that one is y equals square root of x. So I'm going from y equals 5 to y equals square root of x. Those are the two, like from the middle and the outside of that circle. So if I just subtract those two things, then that's the radius. I want them in terms of I want them in terms of y's. This one is this thing right here. So this is just 5 minus y. So the radius is 5 minus y, because this distance from here to here is just y, and this distance from here to here is just 5. And so if I subtract 5 minus y, I find the distance of my radius, and it's in terms of y's, so I don't need to switch anything. Everything's going to be in terms of y's. We're good to go. All right, we need the height. The height would be, well, that would be this distance here. Let me put it in like red or something. That's the height right there. The height is horizontal, so it's in terms of x's. So if it's between two things, I have to subtract the two things. So just like in our previous example, it's going to be x big minus x small, right? I'll do xb minus xs. My s and b look the same, so I'll do big and little. How about x big minus x little? I need to subtract the two x things, but they have to be in terms of y's. So the bigger x1 is over here, which we already said was the y equals 1/2 x, or x equals 2y. That was the bigger x value. Smaller x value, remember we did over here, it was the smaller x value over there is y equals square root of x, which when I solve for x was just y squared. And so if I subtract those two values and put them in terms of y, then I get the bigger one, which is 2y, minus the smaller one, which is y squared, and then I get dy. You might want to compare, oh, and then I have to integrate. I have to integrate along all possible y values. The smallest y value is 0. The biggest y value is of our region, not of the whole thing, right? The axis of revolution is up there, but of our region, of all our slices, the tippy top slice is up here when y equals 2. So what I was going to say before I realized I forgot the limits is you might want to compare the one where we revolved around y equals 0 and the one we revolved around y equals 5. It's almost the same, right? Everything's about the same except that the radius changed, right? The radius was just y before. Now it's a different radius because we have to subtract two things to find the radius. And that is how you do the shell method. That is the shell method. I do have a couple more examples here to show you right here, or I guess one more example to show you right here. I'm going to find the volume of the solid formed by rotating this region and the x equals 0 around the x-axis. And then I'm going to show you, in this particular case, why the shell method is actually better than this method. For a lot of problems, you could do either this method or the shell method. A lot of people do this method because it's like always in terms of x's, not always, but oftentimes in terms of x's, and they kind of like know that, familiar with that. But here's an example where like it's actually going to be easier doing the shell method than the disk method. If you want to explore that, this is a good time to pause the video, graph these, see if you can draw in the region and the revolution, try to find a volume of a slice, add them all up, see what you get. If you want, you can do it using the shell method, which is going to be easier, and you can look at it using the disk method and maybe get an idea of why that might be more complicated. All right, so I'm going to do this now. So if you want to pause and then come back, and I'm going to be doing it. So I need to graph these equations. So this is 4 minus this thing right here. So I think I've typed that in already. Move me over there again. Turn all of you off. Here's this. Here's the 4 minus this thing and the x equals 0. Okay. And then I'm going to just remember the hardest part of our graphing is getting a good picture. So if I zoom out, the only two things that are bounding this are the x equals 0, which is this blue vertical thing, and the x equals 4 minus y plus 3 squared, which is this sort of sideways parabola. Notice the sideways parabola is not even a function, right? Because it has two y values for a given x. Doesn't matter anymore, right? We're going to do it anyway. We're going to find the volume of this thing revolved around, what was the line again? Revolved around the x-axis. Okay. So I'm going to draw a little picture of it so I can show my work. This is 0, -1, and 0, -5, and -3, 4. Am I going to remember all those? Probably not. Okay. -1, -5. Okay. And +4. -1, -5, and +4. And then I think I get something looking like this. Maybe I can draw it. I'll use a different color to make it maybe easier. We don't care too much about like how far it goes because our region stops there. Okay, and we're revolving this around the x-axis. The x-axis. The x-axis is right here. X-axis. Okay, I gotta be on cat duty real fast. I'm gonna pause this. Yes, I hear you, babe. Okay, sorry about that. All right, so we are going to first use the shell method. To use the shell method, I need to slice my region parallel to the axis of revolution. So it'll be a slice like this. And I need to revolve it around. So the distance from here to here has to be the same as the distance from here to here. So I get sort of a mirror image of my rectangle slice over there. And then I'll just kind of make this 3D-ish by making this like kind of circular. to find the volume of a slice, I'll do 2 pi RH times the thickness. Because I sliced it horizontally, the thickness is dy. So I need to find the volume of my slice. I need to find the radius and the height. The radius is always from the middle, the axis of revolution, to the region. So that distance right there, that's a vertical distance. It goes between, y equals 0 and the y for the function. So it just has to be a value of y. So the radius is going to be a value of y, which is okay because it has to be in terms of y since we have a thickness of dy, right? And then I need a height. So the height of this thing, well, the height of this region, this rectangle, goes from here to here. It is an x distance because it's horizontal. It goes from here to 0. So the x big minus 0, just the x value. So the height is going to be x. And then the thickness is dy. Now we know what x is. X is this critter right here. So we're going to put in that thing for x. 4 minus y plus 3 squared. That's the x. The y is a y. The 2 pi is a 2 pi. The dy is a dy. And I need to anti-differentiate this. I need to integrate it to find the total volume. And I need to do it over all possible y values. So the y values, the tippy top slice is up here when y equals -1. The very bottom slice down here is when y equals -5. So we're going to do from the lower limit, which is -5, to the top limit, which is -1. So this is y equals -1 and y equals -5. And that is the integral for this volume. All right, of course, we have to do the math. You have to like square this out and combine the y's together. So there's a bunch of algebra to do. Then you have to anti-differentiate. And you plug in a couple numbers. You plug in -1 and you subtract them and you plug in -5, and then you get the result. So I did mention that this problem is going to be harder using the disk method. So why is that? Why is that? You may have already seen it if you played around with this for a little bit, but I will show you. So -1, -5, just redraw it real quick. This is a +4 over here. Boom, boom, boom. We're still revolving around this axis right here. So to do it using the disk method, this is the shell method up here. To do it using the disk method, we need our slice to be perpendicular to the axis of revolution. So this is the perpendicular slice. Our axis of revolution is right here. And so perpendicular would be here. Our thickness is now going to be dx. It's not going to be dy. And if we revolve this thing around here, we need a distance from here to here to be the same. So it's like a mirror reflection. So we get like a mirror image of our slice going like this. And if we want, we can draw in some circles sort of so we can see what's going on here. So that's sort of the inner circle, which is the hole. And here's the outer, so that's like a disk inside of a disk. Some people call it a washer method. So whatever you want to call it, it's going to be the pi r squared for the outside or for the big one and minus the pi r squared for the small one. So the volume of a slice is going to be pi r squared, but the big one times the thickness minus pi r squared for the little one times the thickness. More space here so that's possible to read. Thickness. Okay, we already know what the thickness is because thickness is dx. We already determined that. So our thickness here, that one there is going to be dx, same as this one over here. And now all we have to do is find the bigger radius and the smaller radius. So radii are always measured from the center going to the out, as far as we can go to the outside. So here's the center, the axis of revolution. And if I go all the way to my function, my region is down here, right? So if I go to the bigger one, it's all the way down here. So that's going to be a vertical distance, which is in terms of y's. So I have to have the y of this function. So the y of this function right here, I'll call it y big, right? That's got to be y big minus 0, just y big. So the big thing here is the radius big is the y, the big y value, squared times dx, pi r squared times dx, minus pi. And the little one, the little radius is from here to here, which is this y little, going to 0. So it's going to be our little y squared times dx. Everything's got to be in terms of dx because, our differential is in terms of x. So everything's got to be in terms of x's. So we need to convert this y thing here and here into x's. So we're going to have everything in terms of one variable. So what is this big y function? Well, if we look at our thing, the big Y function is this 4 minus Y plus 3 squared. So this is 4 minus Y plus 3 squared. And what is this top one? Well, that's actually the same formula. Y equals 4 minus Y plus 3 squared. So something's funny going on here because they're clearly not the same Y distance. This one's bigger. This is the bigger one. This is the smaller one. They can't be equal if one's bigger and one's smaller. So what's going on here, right? So like, why is this happening the way it's happening? The problem is this is not a function, right? So you're going to have two different y values for a given x. So when I have this thing right here, x equals 4 minus, oh, I wrote it the wrong way. My bad. Anyone notice that I switched the variables? It's getting late for me. I guess I should take a rest before I do some more videos, but I'm going to power through this one. I will show you once again the equation. The equation up here is x equals 4 minus y plus 3 squared. X equals 4 minus y plus 3 squared. All right, let me change the other one down here. They're the same equation anyway, right? I got a little ahead of myself, but this is x equals 4 minus y plus 3 squared. In any case, it doesn't make sense to subtract those two guys. They're exactly the same. One cannot be bigger than the other. But as I was mentioning, we need to have the x of these things, and it's not a function, so we need to have like two different versions. We're going to have like a plus version and a minus version, and that's going to be a little confusing. Like, how do we do this? I recommend don't doing it, right? Because it's confusing, it's difficult. If you use the shell method, it's very straightforward, right? You just do 2 pi RH times the thickness. The radius is the x distance, and the radius is the y distance, and the height here is the x distance. So the radius was just y, the height was just x. Our slice of our region made it dy. So all we have to do is change this x into y, and it's given to us right away. So I can change x into y, and I can do the calculation. So anyway, so I just wanted to show you an example where I believe it can be argued quite convincingly that the shell method is easier for this problem than the disk method because it goes between two things. We have to worry about like a plus branch and a minus branch, so you have to break this up into like a piecewise kind of thing and find two different washer methods. It's just a lot of work. I recommend for this particular problem use the shell, but for any particular problem, you want to kind of think about, can I just choose whatever because they're both going to work out fine? Or does one method work out substantially easier than the other method? Because that will be the case on some of your homework problems. All right, well, I need to end it there. That is the last of my examples for 6.3 for the shell method. Hopefully this video was helpful for you. And if you have any questions, please do contact me so I can help you some more. All right, well, I hope you have a nice day.